Hello and welcome to my talk, Unsupervised Classification of KSTAR ECEI Data. Before I begin, I would like to acknowledge my colleagues Michael Churchill, Zhong Choi and Minjun Choi, and also acknowledge our funding sources. The motivation for this work comes from the observation that fusion experiments keep collecting ever larger sets of measurements. And with deep learning, we have a machine learning technique whose performance keeps scaling with dataset size. Fusion experiments produce a significant amount of data, and that amount will only ever increase. In full operation, ITER will generate 2 petabytes of data per day, distributed among its battery of diagnostics. KSTAR, as an example of a long pulse device, produces on the order of terabytes of data per day, and NSTX in 2016 produced between 1 and 5 gigabytes of data per day. A significant amount of measurements, however, are really only ever written, but never analyzed, and there are numerous reasons for that. For example, there may not be an automatic post-processing pipeline a certain data source feeds into, or some data may just not be relevant for a scientific study that was conducted during a run. But it could also be that some data is just never found. And in light of upcoming long pulse devices, automatic data labeling and extraction capabilities become desirable. Now, deep learning is perfectly capable of utilizing big data produced by fusion experiments. Recently developed big machine learning models, for example the natural language model GPT-3 or DALL-E, which generates images from a text prompt, have been trained on terabytes of data. And I'm showing you 2 plots on the right here. The left plot shows the error of models trained on language processing tasks as a function of training dataset. This is from Baidu Research, one of the biggest machine learning research organizations in China and worldwide. They show that deep learning models' performance increases as a power law well over 5 decades increase in training dataset. This sentiment is represented by the plot on the right, which shows that the performance of deep learning just keeps increasing with dataset size, while the performance of more traditional machine learning models will eventually stale. The current state of the art of using deep learning for fusion tasks relies on supervised learning, which requires large amounts of labeled data. Here you see examples of recent studies that use supervised machine learning for fusion tasks. Work performed by Jalalvand and his colleagues, published in 2022, used reservoir computing to detect alphen eigenmodes in ECE data at D3D. This model was trained on data that required manual labeling of alphen eigenmodes in the time series. According to the authors, this took about 1 week. Work published by Bustos and his colleagues in 2021 uses spectrograms to detect MHD activity. They also rely on manually prepared training data. In particular, they manually prepared and labeled 500 spectrograms in an image editor. Kate's Harbeck work on disruption prediction, which uses recurrent neural networks, also relies on a large number of labeled training data. In total, the training dataset comprises about 10,000 manually labeled shots. There is some work to alleviate the reliance on manually labeled data. For example, Montes and his co-workers proposed to use a technique called label spreading to propagate labels from a small subset of the training data to the entire dataset. The work we present here uses unsupervised learning, which does not require any labeled training data. Thus, it promises to free up the time used for labeling data. And most important, this may help unlock the scaling of deep learning with dataset size for fusion tasks. With this motivation at hand, let me present you the outline for the rest of my talk. First, I will give a primer on unsupervised machine learning. Then I will present our work of classifying MHD phenomena observed by the KSTAR ECEI diagnostic, starting by describing the dataset we work on. I will continue by describing 2 unsupervised machine learning methods used to classify the dataset. The first one is based on generative adversarial networks, or GANs. The second one is based on divergences and combines convolutional neural networks with clustering. After that, I will give you some takeaway messages and discuss future directions of this work. Without any additional information on the datasets, unsupervised machine learning models need to identify some structure within a dataset. This can be used, for example, to group the data into different groups, that is, clusters. Or more concrete, the data distribution P of X contains some information so that a classifier can calculate a probability that it belongs to one of K clusters with great accuracy. There are numerous clustering algorithms, and on the scikit-learn website, for example, is this nice overview how such clustering algorithms perform on various datasets. Besides performance on these test cases, there are other issues with traditional clustering algorithms. First, their computational complexity and memory demands usually scale unfavorably with dataset size. To work with big data, they need to be modified. And second, many rely on the Euclidean distance to separate classes. As this metric becomes blurred when working with high-dimensional data, that is the curse of dimensionality, they become unsuitable for images. Common deep learning architectures used in unsupervised learning included, for example, the autoencoder. They learn to map data onto itself and thus don't require user-provided labels. Samples here are mapped onto a latent compressed representation by an encoder and then expanded onto the original size using a decoder network. Other deep learning architectures used for unsupervised learning include generative adversarial networks, diffusion models, or flow-based models. These are typically used to model the data distribution of the input data. For high-dimensional data, such as images, convolutional neural networks learn a hierarchy of features that describe the input data and have been used for numerous downstream tasks, such as labeling, segmentation, and so on. Research on using architectures for supervised techniques for clustering is a novel area in its infancy and an ongoing area of research. In the following, we explore if such models are suitable to cluster ECEI data. Let's continue by looking at the dataset we use for our study. We are working with KSTAR's ECEI data. The ECEI diagnostic has been widely used to study MHD phenomena by measuring temperature fluctuations. At KSTAR, the diagnostic views the plasma at two toroidal locations, sampling 24 by 8 pixels in the radial poloidal plane at each view with a megahertz sampling rate. This produces a data stream of about 1 gigabyte per second and is one of the largest data producers at KSTAR. ECEI measurements have been used to investigate several MHD phenomena, helping understand the mechanisms behind fast and slow sawtooth crashes or how electron temperature is exchanged between a magnetic island and the background turbulence. A review article by Hyun Park from 2019 gives a comprehensive overview of these applications. Our work aims to perform unsupervised classification of ECEI images. For this, we compiled a database of 18 shots where various MHD phenomena were visible. 5 shots show 3 2 magnetic islands, 12 shots show 2 1 magnetic islands, and 1 shot has elm filaments visible. The length during which these phenomena are present varies between a half and 5 seconds among the shots. And as a first step, the data is subject to a bandpass filter, normalized to its mean and clamped to a 15% fluctuation level. The movies you see on the right visualize the various MHD phenomena we aim to classify. The 2-1 islands span the entire ECEI view, while the 3-2 islands are smaller and rotate much faster than the 2-1 islands. The elm, on the other hand, shows up as a chain of crests and valleys, traveling slowly poloidally upwards. I would also like to point out that the data is best understood as a sequence. That is, our brain intuitively connects patches visible in one image to patches in the following image, which have the largest overlap between them. Later, our machine learning architectures will use this observation. To make this data useful for machine learning, we standardize it to unit range between -1 and 1. Looking at the histograms, we see that they vary in shape between the phenomena, but all are unimodal and symmetric. During experimental operations, some ECEI channels may be defunct, causing bad values. We have manually imputed this data using linear nearest neighbor interpolation. As for the other shots not shown here, the frames and histograms look qualitatively similar. Alright, with a well-defined dataset at hand, let's start exploring unsupervised classifiers. We start with an approach based on generative adversarial networks. Generative adversarial networks, or GANs, were introduced as a model that allow the pointwise sampling of arbitrary data distributions. That is, once trained on a dataset, a GAN allows to produce new samples from this dataset. The images you see here below illustrate this. They are not images of real persons, but produced by the StyleGAN2 model, which was trained on a large dataset of portrait images. That is, a portrait image is a single element of the distribution function, and these are high-dimensional samples. The dimensionality given by the product of the width and the height of the image in pixels and the number of color channels. In particular, GANs learn a mapping from a user-defined random distribution to this space. Some recent work studies how this mapping captures features of the data space, such as glasses, hair length, etc. This leads to interesting applications in science, for example by learning salient features in a group of images. GANs were introduced in 2014 in a seminal work by Goodfellow. The central ingredient they feature to enable sampling from a data distribution is to have two models, a generator and a discriminator, that each try to outsmart the other one. Now, as illustrated on the last slide, the generator is just a mapping from a latent random distribution onto the space of the data samples. In tandem with the generator, the discriminator is tasked to distinguish these fake samples from real samples. It outputs a probability, 1 being sure it is a real sample and 0 being sure it is fake. During training, it is known whether a real or a fake sample is provided to the discriminator. Based on this, a score or a loss can be calculated and used to update the weights of the generator and the discriminator using propagation in combination with stochastic gradient descent. During training, the generator and the discriminator have opposing objectives. The discriminator wants to beat the generator, maximizing the probability of outputting 1 for real data and 0 for fake data, and the generator is just trying to achieve the opposite. Training in tandem then leads to ever more realistic looking samples from the generator as it learns the salient features of the data distribution. Here the connection to classification is clear. The discriminator is just a binary classifier. But instead of binary classification, our tasks requires classification over multiple classes, and the vanilla GAN approach needs to be modified for this task. A reason for this is the way that the discriminator is trained. It learns to distinguish between features present in the dataset and absent in the output of the generator. But these features do not need to align with the defining attributes of the classes that the data should be assigned to. Our work introduced by Springenberg in 2016 proposes the modifications shown here. First, the output of the discriminator will be a probability distribution function over all K classes, given by the so-called softmax function shown to the right here. Additionally, the generator now needs to learn the real features for the available classes, while D needs to learn how to distinguish the features picked up by the generator from the real features of the classes. The mathematical means to achieve this objective is given by the Shannon entropy H of a distribution. When a distribution is strongly peaked, its entropy is large. On the other hand, a flat uniform distribution is characterized by a large entropy. The image on the right shows the proposed approach training this model. Presented with a real image, the discriminator should be fairly certain of the class that it belongs to. Thus, it outputs a peak distribution. And presented with an image generated by the discriminator, it should be maximally uncertain, outputting a broad probability distribution with large entropy. And to enable a mapping from sets of features in the image to the classes, all classes should be utilized equally by the discriminator. This mechanism leads to the following formulation of the loss function. For the generator, the marginalized entropy should be maximal. The expected value of the sample entropy coming from the discriminator using real data should be minimized. And the expected value of the entropy coming from the discriminator using fake data should be maximized. Let me note in passing here that a cross-entropy term is used in the vanilla GAN can be added to the discriminator loss function for the case that data labels are actually available. And finally, the loss function for the generator also includes the term for the marginalized entropy so that the generator learns to produce samples from all classes equally. The second term is again the generator being rewarded from outsmarting the discriminator. To implement the proposed GAN architecture for ECEI data, we need to find a suitable architecture. In our experiments, we found that shallow convolutional architectures, which have a few consecutive convolutional layers, perform well. Starting with the discriminator, we need to define an architecture that maps a sequence of 8 ECEI frames to class probabilities. This is done by 4 consecutive convolutional layers. These increase the channels from 1 to 16 to 32. After the convolutional layers, the output is flattened and successively reduced to a 3-dimensional output. Each element of this output vector will then encode the probability of a sample belonging to one of the 3 kinds of MHD phenomena. In the next to final layer, we also apply mini-batch discrimination. This layer avoids mode collapse in the generator and works by measuring the distance between samples in a mini-batch during training, appending the output to the fully connected layers. The generator, on the other hand, defines a mapping from a latent space to a sequence of 8 consecutive ECEI frames. It is defined by a series of transposed convolutions immediately followed by convolutional layers. The kernel sizes, strides, and padding are chosen such that the output dimension corresponds to the samples from the dataset. Our experiments show that this architecture performs better than one consisting only of transposed convolutions, symmetric to the discriminator. Overall, both models have approximately 1 million free parameters. Training the model, we find that multiple metrics need to be considered when determining the performance of a model. First of all, the cluster accuracy should be high. This is shown in the plot of the upper left, where the transparent lines are the actual measured accuracy and the full lines are an exponential moving average. The x-axis is in output steps, where one step corresponds to 25 mini-batches. A well-trained discriminator should also yield higher entropy for the fake data than for the real data. This is shown in the lower left, where eFake in orange denotes the entropy of the fake data and eReal in blue denotes the entropy of the real data. In the right column, we show histograms of the class probabilities output of the discriminator. For the fake data, in the upper right, the histogram appears rather broad, with no sharp peaks. That is, the discriminator outputs no peaked class assignments for generated samples. For real data, shown in the lower right corner, the histograms are peaked at 0 and 1, corresponding to peaked histograms. And of course, generated ECEI frames should look similar to real data. Output on the right appears similar to 2-1 island and an Elm perturbation that appears in the training data. Overall, we scanned the architecture over different batch sizes, varied learning rates for the discriminator and the generator individually, changed the number of channels, varied the degree of semi-supervision in the loss function, varied the latent dimension, and the leak rate for the leaky ReLU nonlinearities. In total, we scanned a performance over 216 runs. Overall, we find that the GAN can cluster the ECEI sequences reasonably well, with cluster accuracies on average of about 70%. During training, individual models achieve over 90% accuracy. To compare, the authors of the original paper achieve about 98% accuracy on this relatively simple MNIST dataset and about 80% accuracy on the more complex CFAR10 dataset. Here, the original paper performs semi-supervised learning, similar to our cases for values of lambda larger than 0, as shown here. The most relevant hyperparameters in the architecture used are the batch size, the degree to which available labels are used, and the leak rate of the leaky ReLU activation function. Here we show cluster accuracy over the runs grouped by these parameters. Transparent regions give a min-max range. So, we just saw how to use GANs to cluster a sequence of ECEI frames. Let's continue by investigating how well a different architecture, based on divergences, performs this clustering task. First, let me introduce the notion of a divergence. Simply put, divergences measure the separation and compactness of distributions, and these are properties intuitively linked with clusters. Here you see the Cauchy-Schwarz divergence, evaluated using two Gaussian distributions with different parameters. In particular, the upper left shows the situation where the distributions are well separated and rather compact. When we imagine to draw samples from these distributions, we would imagine that the resulting clusters are rather easy to separate. The other plots show the situation where the distributions are either not separate or not compact. Again, when we think of drawing samples from these distributions, we would expect the samples to have a large degree of overlap, so it would be difficult to tell the clusters apart. Calculating the Cauchy-Schwarz divergence for these cases, we see that for the separate and compact case in the upper left, the Cauchy-Schwarz divergence is approximately 1 order of magnitude larger than for all the other cases. That is, a large divergence corresponds to separate and compact clusters. To cluster our ECEI dataset, we use the deep, divergence-based approach to clustering introduced by Kampfmeier in 2019. This paper proposes a model that combines a deep convolutional neural network with clustering into an end-to-end trainable model. The loss function includes an estimate of the class divergence and thereby aims to minimize the separation and compactness between the clusters. In particular, the model learns a set of hierarchical features through its convolution layers. Together with these features, a final layer produces class assignments, again using a softmax output layer. Together, the cluster assignments and the final feature layer are used to estimate the Cauchy-Schwarz divergence over the assignments. Additionally, the loss function uses information about the output geometry induced by the softmax output. The softmax induces a simplex. For 2 classes, this is a line in 2D space. For 3 classes, this is a triangle in 3D, and so on. 2 additional terms are then computed, which respectively push softmax assignments to vectors to the corners of a simplex and favor orthogonal cluster assignments. In total, we scan this model over 144 different configurations and observe a cluster accuracy of approximately 65%. The most important parameters identified in our scan are a learning rate, which is optimally set to 10 to the negative 4. Also, a batch size of 256 performs best while there is little sensitivity to the size of fully connected layers, the number of channels, and the length of the input sequence used. These numbers are comparable to the performance described in the original paper. In addition to standard datasets, the authors tested their model on datasets consisting of images of different types of seals on sea ice background, and the task was to classify the kind of seal. Here, the authors list a 75% accuracy for a dataset with 2 types of seals present and 56% for 3 kinds of seals present. Good. Now please let me conclude, giving you some takeaway messages from this talk and outlook for future work. First, unsupervised deep learning promises to tap into deep learning scaling of performance with dataset size, while avoiding expensive data labeling tasks. Unsupervised or semi-supervised deep learning is not a well-explored field, and many promising approaches have been proposed in the last couple of years. And this work presented here is an early attempt to characterize their potential for fusion applications. And indeed, we find that some unsupervised deep learning architectures can be trained to cluster ECI data in an end-to-end fashion. Most unsupervised deep learning techniques rely on information theoretic concepts, such as entropy or divergences. And with this, they have their own unique constraints, for example, the balance among the classes as discussed for the GAN. Both approaches shown here, the GAN and DDC, can approach 60 to 70% cluster accuracy on the ECI dataset of MHD phenomena. As for future work, we are currently looking at the interpretability of the cluster assignment models, and we are also looking into more recent developments in self-supervised learning. If you are interested, please follow the link provided here or in the QR code to the GitHub repo with the code, and feel free to contact me. Thank you for your attention. I'm looking forward to hear your comments and questions.